All right, so we are going to talk about the first law of thermodynamics. This is a conservation of energy principle, okay, taking heat into account. Okay. And I'll just show you the law before we get into. Okay, so here's the first law of thermodynamics. Okay. This is internal energy. This is heat, and this is work done. Okay. So let's look at each term. So let me show you an example. Yeah, there you go. Okay, so here's a solid. Let's say this solid is at room temperature. What is the internal energy? Well, what's happening in this solid from an atomic perspective? What's happening to these atoms? They're vibrating, okay? So they have random kinetic energy. These interatomic distances are longer than at a lower temperature, so they have potential energy as well, okay? So they're expanding in random directions and stuff like that. So there's random kinetic and potential energy, okay? And the sum of all that is internal energy. Okay, did you guys understand? Okay, so if I take this solid and bring it in contact with the solid at a lower temperature, what happens? Some of this internal energy shared goes over there, and that is heat. Okay? In this gas, what is internal energy? I'm sorry? Okay. It's just this random kinetic energy. Okay, there's no potential energy. This is an ideal gas. Okay, so internal energy is that random energy. Okay, so now let's look at that formula. Okay, so the thermodynamics, first law of thermodynamics states the following. Okay, if you add heat to a system, here's a system. If you add heat to a system, and if the system does this much work, okay, to do work you need energy. Okay, so if you do this much work, let's say I add 100 joules of heat and I do 40 joules of work. So this statement is saying 100 minus 40 is 60. The internal energy increased by 60 joules. That's all. It's as simple as that. Okay? So once we realized that heat was a form of energy, you needed this. Okay? Okay. So this is a conservation of energy principle that's taking heat into account. Okay. So again, so did you guys understand that? Okay, so this is just a conservation of energy statement. Okay. And we'll apply this to various processes. We'll learn to apply this to various processes. Okay. So that's the first law of thermodynamics. Again, what is it? A conservation of energy principle. Okay. All right, so now let's learn some terminology. Okay. So internal energy or thermal energy of the system is the random internal kinetic and potential energy. So here's a solid. At any temperature, these guys will be vibrating randomly. Higher the temperature, greater the amplitude of vibration. Okay. So internal energy is the sum of random kinetic and potential energy. Okay. So for instance, if I take this phone and move it like that, did its internal energy increase? What's that? Right. No. Its internal energy didn't increase. Okay, It's macroscopic external energy increased. Okay. All right. Heat can be used to do work. Okay, so you can use heat to do work. Now, the second law of thermodynamics will tell you that if you have 100 joules of heat, you can't convert all of that to work. Okay, there's a maximum amount you can convert to work. Okay, and so your car, how much, what is the efficiency of your car, or how much heat can your car convert to work?
30%.
I'm sorry?
30%.
20. Okay. Roughly the most efficient heat engine we have is a thermal power plant. Okay. And that's 40% efficient. Okay. What happened to the other 60%? I'm sorry? Stays as heat. Okay, so heat is the worst form of energy. Okay, so we'll learn that next chapter. Okay, so so heat can be used to do work. Okay. What is a thermodynamic system? We learned about that. What is a thermodynamic system?
A system of heat is being transferred.
Any system which has a large number of particles. Okay. And what do we mean by large number of particles?
Mole number of particles.
Yes, so roughly of the order of moles. Okay, so we're talking about billions and billions of particles, 10 to the power. Okay, so here is a thermodynamic system, here is the boundary of the system, and here is the surroundings. Okay. Now, if the system is isolated, that means it cannot exchange energy with its surrounding. Okay, it's not interacting with its surrounding. Okay, so we will mostly deal with closed systems, but eventually you will deal with open systems as well. A system is open if the number of particles changes in the system. Okay, that's it's exchanging particles with the system. Here is a closed system where the number of particles in the system is constant. Okay. Are you an open or a closed system?
Open.
Oh, I'm sorry?
Open.
Open system. You're exchanging oxygen and carbon dioxide with the atmosphere. Okay. And among other things, you're also eating food and stuff like that. All right. Reversible processes. Okay. A reversible process is one in which the system and the surrounding can be returned to the initial conditions from the final state. Okay. So what we mean by that is the following. Okay. So let's go to this. Okay, so here's our system, for instance. This is a closed system. Okay. What I'm going to do is I'm going to light a fire outside and heat this gas. Okay, and you can see that the temperature rose from 300 degrees to that. Now the question is, okay, I'll cool the gas and cool it back to 300 degree Kelvin. Okay, I cooled it back to 3. Now, if the surrounding also went back to its initial state, then that's a reversible process. Did you guys understand that? So if I can take the system and the environment back to its original state, then that process was a reversible process. Okay. Well, so this is just an idealization. All natural processes are known to be irreversible. Okay. So you can cook a pizza, okay, and it turns out that you can never uncook a pizza. Okay. Well, you can freeze water. Okay. How do you freeze water? You remove heat from it, and then you can unfreeze it again by adding heat. Except that the surrounding environment has changed, so you can never go back to the original state of the universe. Okay. All right. So, but this concept of reversible processes is useful in setting upper limits. Okay, so when you want to set So for instance, if you ask questions like, what is the best you can do with a heat engine? We'll, an ideal heat engine, and we'll use reversible processes there. Okay? So you guys have heard of Carnot engines? Carnot engines are ideal heat engines, and that tells you what is the maximum efficiency you can have when a heat engine operates between two temperatures. Okay. Let's see. All right, so when I lift an object up, I've done work on it. Okay. And so when I lift an object up, so for instance, here's an object, mg is the weight acting, and I've applied a force equal to that. And if I lift it through a height h, the work done by me is mgh. I've done that much work. Okay. All right. So here's the point. So here's a gas in a cylinder. What I can do is I can put a weight on top of the cylinder, and then I'll heat the gas. And when the gas expands, it'll lift this object up. Okay. So expanding gas can do work. Okay. And so this goes to the derivation. The amount of work this gas does when it expands, when this piston moves a distance dr, is the force that the gas exerted times dr. Force is pressure of the gas times the area of this piston times dr. And that is equal to the change in volume of the gas. Okay, so when the gas expands by that amount, and the gas is at that pressure, that's the amount of work done by the gas. Okay. When dV is negative, meaning the gas compresses, the gas has done negative work, meaning you have done work on the gas. Okay. So when the gas expands, it does work. Okay. So the sign convention is work is positive, and in some books they take the opposite sign convention, so you need to be aware of this. Work is positive when the gas does work, and negative when if work is done on the gas. That's the sign convention the book we use adopts. Okay. Okay, so this is the amount of work done when you have the gas expands a small amount. All right, before I go into that, let me show you something. All right, so here's our gas. Okay, so again, this gas is at 300 degree Kelvin, and there's the pressure at 24 atmospheres, and so on. Okay, and so what I'm going to do is I'm going to heat this gas. And the volume is going to be constant. Okay, so what's happening to the pressure? It's increasing. Okay. All right. So you saw the process. Okay. So here's a very neat way to show this. Here's a pressure versus volume. That was the initial state of the gas. Okay. And I heated the gas at constant volume. And what happened? The pressure increased. Okay. And there is the final state of the volume. Okay. So when you're working with gases, it's very useful to have these PV diagrams, meaning diagrams on a PV chart. Okay. So for instance, I can do a process where I'm increasing the volume and increasing the pressure. Okay. And so on. So, well, I don't know if I'll be able to do this here. Okay. So, oops, I didn't want to do that. All right, I can't change the volume. Okay. Stop punch. Okay, with. No, I can't change it. Anyway, so you can do various processes to the gas and show them on a PV diagram. Okay, so what is this process?
Pressure remaining constant and expanding the volume.
Yeah, so how would you do that? Can you think of, so take a balloon and heat the air in the balloon, and the pressure is constant and the balloon will expand. Okay, and stuff like that. Okay. All right, so this is very useful. So what is this process, for instance? Here's a process. Okay. The gas is expanding while the pressure is dropping. Okay. All right, so there